In the late 20th century, the semiconductor industry found itself boxed into a corner. The digital revolution, the process of making computers smaller, faster, and cheaper, was operating on a massive assumption about the future. Engineers had grown accustomed to a very specific rhythm. The number of transistors that could fit onto a microchip roughly doubled every 2 years. This observation, Moore's law, acted as the strict roadmap for the entire industry. To keep hitting that target, manufacturers relied on a process called photolithography. Deep inside highly controlled cleanrooms, light is beamed through a mask containing intricate circuit designs. That light then projects those patterns onto a photosensitive material coating a silicone wafer. But there is a strict physical limit to this process. The smaller the features you want to print, the shorter the wavelength of light you need to use. The world was demanding smaller transistors at a relentless pace. But the actual physics of light was beginning to push back. For decades, the industry survived by simply inching its way down the electromagnetic spectrum. Manufacturers evolved their lithography systems from visible light down into ultraviolet light, allowing engineers to consistently shrink these structures. By the 1980s and 1990s, however, a wall was approaching. Future chips were going to require structures measured in mere tens of nanometers. Traditional optical systems were straining against their physical limits. Researchers across laboratories in Europe, the United States, and Japan started looking for a radical alternative to break through this barrier. They landed on a strange region of the spectrum called extreme ultraviolet, or EUV, which has a microscopic wavelength of just 13.5 nanometers. On paper, it was the exact solution required to keep Moore's law alive. In reality, everything about EUV appeared completely hostile to engineering. The first problem engineers faced: no ordinary light bulbs are capable of producing useful EUV radiation. Generating this light required inventing an entirely new, highly violent process. It relies on microscopic droplets of liquid tin, smaller than the width of a human hair, fired continuously through a vacuum chamber at astonishing speeds. High-powered lasers are timed to strike each individual droplet twice. The first pulse flattens the droplet into a disk. The second pulse vaporizes it entirely. For a fraction of a second, the resulting plasma reaches temperatures exceeding hundreds of thousands of degrees Celsius, hotter than the surface of the sun. Inside that extreme environment, EUV photons are finally emitted. Producing the light was only the beginning. The radiation that came out of this plasma was extremely weak. Most of the generated energy never converted into useful EUV light, meaning enormous laser systems were needed just to create enough illumination to manufacture a chip. Then came the optics problem. Even if you can generate EUV light, you still have to focus it to print the patterns. But conventional glass absorbs EUV completely. Lenses were totally out of the question. The machine required mirrors instead. The issue was that ordinary mirrors absorb the radiation just like glass, reflecting almost none of it back. Scientists invented the multi-layer Bragg mirror, dozens of alternating atomic scale layers of materials like molybdenum and silicon. But each mirror reflects only 70% of the light. Bouncing across multiple mirrors before reaching the silicon wafer, more light is lost with every single strike. Engineers had to fight for every fraction of a percent of reflectivity. Even thermal expansion measured in nanometers could ruin the imaging accuracy, forcing the entire optical path to operate under strict, absolute physical constraints. Because even atmospheric gases and invisible dust particles absorb EUV light before it can reach the wafer, these complex optical systems had to operate completely sealed inside massive vacuum chambers. Getting these interconnected systems to work perfectly required decades in the dark. Prototype systems worked in laboratories but struggled to meet the demands of high-volume manufacturing. Throughput was too low, costs were astronomical, and critics argued the technology would never be economically viable. The engineering barriers were too vast. No single company possessed the specialized expertise required to invent the high-power lasers, manufacture the atomic-scale optics, and engineer precision vacuum technologies simultaneously. Instead, thousands of specialized suppliers distributed across numerous countries began to coalesce. This massive, international collaboration slowly organized around a relatively small Dutch company that became the focal point of the effort, ASML. The machine became the result of a vast international supply chain, requiring precision mirrors from Germany, high-power lasers from the United States, vacuum components from dozens of countries to function as a single unit. After billions of dollars and decades of iterative redesigns, the technology finally crossed the threshold of commercial viability. Major semiconductor manufacturers, including industry giants like TSMC, integrated EUV into their advanced production lines. The integration validated the decades of struggle. Circuit features that were previously considered impossible to print became reality, allowing transistor densities to resume their rapid upward climb. Fitting more transistors into the same microscopic footprint directly improves computing performance. Processors execute calculations faster and operate with far greater power efficiency. This microscopic density scales up to power the heavy infrastructure of the modern era. Massive artificial intelligence accelerators and high-performance cloud computing networks only function because these densely packed chips can be manufactured at volume. Modern computing infrastructure is now built on the industry's ability to consistently generate and focus a wavelength of light once thought unusable for manufacturing. Because ASML is the only company capable of building these systems, the technology has created a unique bottleneck in the global economy. Without access to these specific machines, it is physically impossible to manufacture the processors required for advanced defense systems or the largest AI models. This technical monopoly has turned a manufacturing tool into a strategic asset. Controlling the export and placement of EUV systems has become a central objective of national security and economic policy, and the engineering cycle is already repeating. EUV is approaching its own physical limits, forcing the industry to confront atomic-scale variability and quantum effects. Engineers are currently developing high-NA EUV systems to press the boundaries even further. The machines that emerged from the EUV investigation are among the most sophisticated manufacturing tools ever built. They stand as a quiet testament to an industry that repeatedly looks at the absolute limits of physics and simply refuses to stop printing.